This talk will introduce a few mathematical concepts also to reason about when we might be making a decision too fast, when we should not rely on these heuristics that work so well for us in the past, or maybe for 90% of the cases even, but what's the 10% where you should really pay attention? And do we really make our own decisions, or are we guided by our environment or what we learned or heard at a conference? Well, I hope that during this talk you'll hear a few things that will influence your decision making. I like the phrasing of being wrong as well, because it doesn't really assign any blame. It can be that you just ended up wrong because of how you were brought up or the things you learned along the way, and you get the chance to not be wrong the next time. After seeing this talk, you're not going to be not wrong all the time. In fact, that's impossible. We're also going to see that. So don't expect too much out of that. But you are going to learn a few new concepts about where to pay attention. Very briefly, who am I? My name is Berwout de Vries Robles. And with that, I think I sympathize with a lot of you guys because a lot of your names are also quite hard to pronounce for international people, and you will have to spell them everywhere. So I feel your pain there. I work for a company called Open Value. We do mostly Java-based consultancy. Don't hate me. I'm open to changing my stance on capital letters. I work for a company called Alliander. They do the medium voltage power grid in the Netherlands, and that's basically everything below the large power towers you see out in the field. Everything from that down to where it gets into your home. And in the Netherlands, we have a very interesting challenge there, is that we've added a lot of electric vehicles and a lot of solar panels in every house using government subsidies. So the net is actually very congested in the Netherlands. And we're using quite new and innovative solutions, like using our customers as flexibility. So we can ask some factories to use more power when the wind is blowing, for instance. And that sort of day-ahead forecasting and that sort of stuff. It's all things I work on. It's really interesting, but that's not what the talk is about. This talk is based on two books. It's based on How Not to Be Wrong, or Mathematical Thinking by Jordan Ellenberg, and it's based on Thinking Fast and Slow by Daniel Kahneman. And they're books about psychology and mathematics and intuition. I'd like to start off with a quote from the Mathematical Thinking book, because you might think, why do I need math? Well, if you see this quote, the specialized language in which mathematicians converse with one another is a magnificent tool for conveying complex ideas precisely and swiftly. But its foreignness can create among outsiders the impression of a sphere of thought totally alien to ordinary thinking. That is exactly wrong. In this quote, I'd like you to replace the word mathematicians with software engineers, and you will see that it applies almost completely. The way we talk to each other at a conference or during work can seem completely alien to anyone inside the business, to anyone inside of our social lives. But sometimes we forget that software engineering is actually about reality. It's about the things that we are trying to build. And these terms, they can help us convey ideas, but they're not necessarily good or bad. It depends on the context we apply them in. So like mathematics, we need to be careful that we apply software engineering in the right places. From Thinking Fast and Slow, a main concept in the book is System 1 versus System 2 thinking. System 1 thinking is the thinking I described at the start of this talk. So it's an intuition-based type of gut feeling approach where you'll be able to read the room very quickly. For instance, if someone in the second row is looking bored, I know that I'm doing a terrible job, but I can see that quite immediately without having to think about it. For instance, if you had to estimate how many people were in this room, I'd say there's about 60 or 70 of you. That's System 1 thinking, because I've trained that behavior all my life. I kind of know how to recognize a crowd. If I were to apply System 2 thinking, I like to compare it a bit more to software. It's a learned behavior. It takes a bit more time of compute, and I actually get a better result sometimes. So for System 2 thinking, a typical example would be, I would take 5 of the rows in this room, I would count the empty spots there, I would decide, oh yeah, about 0.6 factor of this room is empty. I would count the number of rows, and I would get a better estimate, probably, for the amount of people that are inside this room. So System 1, I like to compare to a circuit board, where you printed in the logic gates beforehand, and all you have to do is you apply some power on one end, and a decision rolls out at the other end. But it takes some time to print that behavior. And we also apply in our work and learn many of these heuristics that turn into circuit boards. We just look at the situation and intuitively we know an answer, right? And for things that are a bit less obvious, we build software. We we design actually the responses that we want from our mind based on the situation we see. But to do that, we need to look more closely at the problem. All right, so about math and software engineering. We already saw the quote at the beginning. I like to visualize software engineering a bit like the traveling salesman problem. Does anybody know the traveling salesman problem in here? Quite a few of you, that's nice. So for those of you who don't, the traveling salesman problem is a very famous math problem where you have a number of cities and the traveling salesman has to visit each of these cities and has to find the shortest route to visit each one of those cities. And it's actually a very difficult problem when you get to a certain city size. You cannot solve it in polynomial time even. You will get an exponential time constraint. And software engineering is a little bit like that, because like the traveling salesman problem, you want to figure out what the shortest route is, but you don't always care about the exact answer. You might develop a heuristic that will give you a 70% right answer, and it might be good enough. So if you want to deliver groceries, for instance, you can divide it up in sectors, and if you get a decent answer, it's probably good enough, because the groceries need to be delivered tomorrow. You don't have infinite time to get the exact correct solution. In software, we have that same problem. We can think about things for a long time, and we'll probably get the exactly right answer. But usually we don't have that freedom. We have constraints of time, we have constraints of budget, we have all sorts of constraints that are pushing on us to get a good enough solution. And our trick is to figure out what is good enough for this specific solution. Another quote from the book, and I promise I'll stop with the quotes then. As a mathematical discipline travels far from its empirical source, or still more, if it is a second and third generation only, indirectly inspired by ideas coming from reality, it is beset with very grave dangers. It becomes more and more purely aestheticizing. So this was a quote also about math, but it's made by John von Neumann, one of the forefathers of computing. And he warns us here that when we start to look at software as well, we run the risk at some point, as we get further and further away from reality, of deciding because something is pretty to us, because it is aesthetically pleasing. And the further away we actually get from reality, the more we run this danger. And for me, that kind of sums up what the meaning of software engineering is. So we hear a lot about making an impact, making the world a better place, delivering value, but all of these things are very vague because depending on what your domain you're in, it will differ completely. And for me, software developing becomes software engineering the moment you actually also start to think about, should this be a software problem? Am I delivering a good enough solution? Or should I think a bit more? Once you take in those constraints of time and of what the actual reality is of the situation, that's where, to me, you start becoming more of a senior engineer. You start to get the discussion between the business. You might offer a few alternatives to say, hey, I can build this cheaper, but it will do it this different way. Or it might do it 12% worse. Is that worth it to you? That's where software developing becomes engineering. Instead of looking at the task that the business demands you do, you look at what value does this create, and do I want to create that value? And actually, one of the most difficult choices of my software engineering career was when I was a software engineer for about 2 or 3 years. And I was working for an educational company, working in primary education. And I was building a system where about 100,000 students in the Netherlands every day, they logged on and they did their math homework. So it's related to the math talk as well, but in a different way. They had an idea, and they liked me on the job. They had an idea to build a recommendation system. And it was back in 2018, 2019 or something. So recommendation systems were actually quite young, and I thought, oh, recommendation system, this is going to be cool, right? And they wanted the recommendation system to figure out a thing called personalized learning. And personalized learning is where you have a child and it gets its own curriculum, basically. So you shape the curriculum based on what you think this child should be doing. And it was very popular in the Netherlands. I'm not sure if it's popular here as well. But the idea is that you can give a more tailored approach to each individual child and they get a better learning result. So the recommendation system's goal was to recommend items on the level of the student's expertise. And the way it did that is it ranked the items in the software based on how previous students completed these items. And then finally, it would recommend a new item to a new student. Now you already see quite a few problems there. One of them is, if I introduce a new item, how do I know which child to recommend it to? I don't really, right? Because I have no idea of any previous students making it. So I'm trying to predict what the score of this student will be on the next item. And then I'm going to give him that item so that he can get his personalized learning journey. So in the research, this looked actually quite good, this personalized learning approach. You would get a weaker student, for instance. They would get a somewhat easier exercise. They would get the feeling of fulfillment from completing that exercise and be encouraged to exercise more. But in practice, in the Dutch market, it's very interesting because if you have a primary school class with 30 children and you have an hour to do math, you're never going to extend past the hour because all the other 30 kids are done and you need to pay attention to them and you need to do language or maybe history or geography. So an interesting thing we found out was that if you recommend weaker students lower exercises, they will actually get stuck at that level because by the time they complete, they also complete less exercises. They will not be up to the level that we expect actually at the end of the lesson. So it turned out that giving them the regular exercises and having them deal with difficulty may have been a better approach. Now I found all that out before I took the job to build the recommendation engine. And why did I find all that out? It's because I was interested. I was interested, if I build this recommendation engine, do these kids actually get a better learning experience or not? And in the end, I turned down the job. Even though it was for me quite an opportunity, I got to lead an initiative if I wanted to, but I didn't want to take the job because I thought these children were going to be stuck at the end of the hour having a worse learning result, and the only positive effect it would be on the sales of the company to be able to say, hey, we use AI in our solutions. Because AI was quite the hype back then already. And as software engineers, we have that choice. It was also something that was illustrated yesterday. During the CTO talk, at some point, there was a controversial opinion that software engineers are overvalued. I think we're in a luxurious market right now. Software engineering is very, very hip, and you can get a job almost anywhere. That also means you get to choose what you want to contribute to or not. And you have the power to say no to some of these initiatives if you don't believe they will actually bring better software. Or if it's even worth solving in software. In this case, it might be better solved just by having the teacher in front of the class pay more attention to the kids. All right, I'll give a brief overview of the topics that we're going to cover in this talk. I'm going to start off with linear thinking, and that has to do with the heuristics we all develop for each other. Then I'm going to talk about Bayesian inference, and that's a very expensive word to say reasoning about chances based on prior observations. Then I'm going to talk about expected value and utility theory, about unlikeliness, and finally about a psychological effect called priming. And we're going to see each of these. They're topics from the books as well. Yeah, they're only part of the topics of the books. So after this talk, I still recommend you read both books, by the way. So I hope I get you enthusiastic to do that. So linear thinking. A typical example of linear thinking you might have seen in management before is the following. I need to get somewhere fast. I'm going to hire more developers, right? And it's a very typical example where you have, we also call this sometimes the 9 women, 1 baby problem, right? You, you need to deliver a baby. One woman delivers a baby in 9 months. So I'm going to hire 9 women and they will bring me the baby in 1 month. It's very simple. So this is a typical example where you think, well, I've been adding developers and my speed has been going up. Probably if I add more developers, my speed will go up even more. And perhaps in actual software output it will, but does it also bring you closer to your target? So in reality, the curve might look a little bit more like this. And your job as a software developer is to point out to management, hey, I think we may be on the wrong end of this curve, and actually giving me an extra developer in the team may not help. It may even harm. And an interesting thing also is that this distribution changes from project to project. So one interesting thing about the current job I work is that they hired all seniors. They thought we're starting a greenfield project. We need to hire all seniors because they know what they're doing. But seniors also have quite a strong opinion. So if you walk into a room of 6 seniors and they disagree with each other, you will find out you end up on the wrong side of this curve quite fast, actually. Another one that's maybe slightly more controversial. So how many of you, show of hands, how many of you think they should write more tests where they're currently working? That's about 80 or 90%. And I think that's actually a valid distribution for the heuristic. Usually, you end up in a situation where you need to write more tests. But I'll give you a specific situation, which is my situation, that there was no previous manual process for this thing where we use customers as flexible solutions inside the energy grid. So we started off not knowing even functionally what the thing was going to look like. And in that case, it can be very expensive to start adding tests too early, because tests, they help you lock in your solution. So they're very great for maintainability if you want to maintain software for a long time and you want to make sure that it doesn't break over time. You can use your automated tests to verify whether that's true. But this software, we didn't even know whether the functional solution was the right one. And in that case, if you lock in your software too much and you start to build these test boxes to make sure that nothing breaks, then the moment you have to change something, all the tests break. And you have to change all the tests as well. So we were actually going slower because of the amount of tests we developed. And you'll find out that maybe the curve for you looks a little bit more like this. And at some point, obviously, you're going to approach a very high test coverage. And you'll find out that the last 15 to 10% is going to be way more difficult than the first 85 to 90%, right? And they might not be worth testing even. And I'll give you an example from my job as well. This is my current quality gate. And how many of you are familiar with SonarQube? Oh, that's almost everyone. SonarQube scans your code and looks at how much code coverage you have, and then you have the option, not the requirement, I want to mention that, to put the gate in place. And what that does is when your CI/CD build runs, it will check whether the new code meets the conditions of this gate, and then it will fill your build. So you will not be allowed to push to production any code that is untested, for instance. So in this job, where functionally nothing was clear, it was sort of like a startup situation, we had a conditional code coverage of 85%. And code coverage regularly just checks whether you hit the line, right? But conditional code coverage checks actually inside your if statement if every value has gone through every different possible solution. So if that value, let's say you have an AND statement, if this value has been false and this value has been true, and the same for the second one. So you end up writing for some pieces of code that you don't even know are functionally correct. You end up writing 36, 40 tests just to meet this coverage gate. And I consider this gate actually to be one of my largest failures, because among the department we had 16 lead developers, of which I'm one, and we had a discussion about whether we should do this gate or not. And I told them, not everyone is going to be happy with this gate. This gate is going to work in many situations, but it's not going to work for the teams that have no clue what they're doing and changing functionality every 3 weeks. The same goes actually for the duplicated lines. Has anybody ever done version control for APIs? Right. One of the common ways of doing version control of APIs is you copy the endpoint and host the version 2 next to it, right? If you don't allow duplicated lines, it becomes very annoying because you have to create some sort of abstract service that decides whether you're doing version 1 or version 2 and then does difficult things in the backend instead of doing the pragmatic thing and copying your endpoint. There are many solutions to this, obviously, so copying is not the only one. But it can be very harmful to have a quality gate like this. And I could not convince the other software engineers on my team that this was harmful. I actually did get it down from 95 to 85%, but they were like, we're a utility company. We have to be sure that the power we're running through the lines is correct. So we need to be correct all the time. So we need a very high quality. And they thought a green gate is synonymous with quality. So be careful there. Another example from my current job. In the Netherlands, we very much believe in Scrum. I don't know how it happened, actually, but we believe that Scrum can be applied anywhere, at any time, in any way. And all you have to do is follow the Scrum guidelines, and you will be great, always. One of the things that they had was we didn't have enough Scrum Masters at the beginning, because these teams were forming, and they were looking at how can we get control of the process. And the problem really was, how do we define the functionality so that we can actually serve these customers? But they thought the answer lies in the process. So what they did is they hired a bunch of Scrum Masters. They came in to join teams of mostly senior developers that were very familiar with Agile and Lean development, that were already running Scrum. And they came into the teams, and the moment they came in, they started complaining. Why? Because in their teams, they were the people who planned the meetings. They didn't have anything to do. During the retrospectives, during the sprint planning, these teams, they pretty much ran themselves. So what ended up happening is they split these Scrum Masters over different teams. So they are meeting planner now for 3 or 4 different teams at the same time. And one effect it's had on us is in DevOps, we like to say that when you manage your own software, you feel the pain, right? And when you feel that pain, you will be motivated to fix it. The same actually goes for meetings. If you never feel the pain of planning a meeting, you will actually prepare less, usually. So what we found out is the Scrum Masters would plan a meeting and all the developers would show up at 9:05 and be like, ah, a retrospective, nice. I don't have to do anything. And that actually is a great recipe for disaster, right? And the second great recipe for disaster there is that these Scrum Masters had a lot of spare time on their hands because these teams were effectively managing themselves. So they now hired people with... So the risk we had was we had software people that lacked domain knowledge, that were building things inside quite a complex domain. And that's a risk we as software developers have quite often, right? We lack knowledge about the domain. What they now had was people they hired that had a lot of free time on their hands, had no knowledge about the domain, and also no knowledge about software engineering. What happened is they start changing things a lot. Because they have so much time, they come up with change initiatives to make the process run better, run faster, every time. And in fact, it was changing so much that by the next week you would have a different process before even being used to the original one. So this is also, it's a form of linear thinking that may not be as obvious. It's a one team needs one Scrum Master solution, right? There's the line. But it's also an X is bad or X is good. So somebody had the experience that Scrum is good in the past because it helped their teams. And maybe they had a team with quite a few juniors that had never worked in an Agile environment before. So they learned Scrum Masters are great. They can help me get my team in order. But in this situation, Scrum Masters were not great. So one thing I like to end linear thinking on is, okay, I promised no more quotes, but this one, only a Sith deals in absolutes. So as a software engineer, we really like to say it depends. And that's because it depends. It always depends on the context that you're in. So this means that if you hear someone say X is good X is bad, more of this is better, less of this is worse, less of this is better. Any of those are a form of linear thinking, and you should be aware that they don't apply under all the situations, and have them mention why they think it applies in this situation. All right, we're going to go on to Bayesian inference. And I'm going to explain this one by starting with a very simple example with a coin. Now you may have, if I start flipping a coin on stage, you may have some pre-existing beliefs about that coin. Let's say you believe it might be a fair coin, and you believe that by about 90%. And you might believe that it has a 5% chance of having a 10% bias to tails, or a 5% chance of having a 10% bias to heads. Now if I start flipping that coin on stage, and I get 5 heads in a row, I'm going to actually observe that under these assumptions, if I would not get 5 heads in a row, I probably have close to that 5%, right? Because that's what you expected. And the other part is left for the actual observation that we saw. So you'll also see that if I toss 5 heads in a row, I'm going to be more likely to be biased towards heads. And actually your bias to tails belief should reduce based on the observation, right? If I'm tossing a fair coin, then the chance of having 5 heads in a row is still quite small. So you might be surprised by the fact that I tossed 5 heads in a row. So given that I tossed 5 heads in a row, we're going to look at this bottom column, and we're going to sum up the numbers that are over here. And you'll end up somewhere on 0.0325, something like that. And then you can calculate, given that observation, what is actually the chance that this coin is biased? That my pre-existing beliefs about the 10% heads to bias to heads, is actually true. So what you do to do that is you divide this number by the total number of the observation that you found. So you found one observation, 5 heads. You divide 0.0039 by that 0.0325. You get about 12% chance. So your belief adjusted, right? You saw me toss 5 heads in a row, and math actually tells you that your belief should be adjusted, that you should now believe that this coin may be weighted towards heads more. And that's actually a logical conclusion, right? But in reality, this only mentions 3 scenarios. And actually, if I flip 5 heads in a row, you're probably very likely to believe that I have a rigged coin. That it's not a 10% bias to heads. You're way more likely to believe that this coin is just completely biased towards heads. And you'll see actually that human belief is spiky like that. So you actually have some pre-existing notions about coins, probably from looking at magicians, right? That the chance that it is heads all the time, that is biased completely towards heads, is rather large. You might believe that I'm a Java consultant and therefore not very trustworthy. So you might assign a 33% chance that I've rigged it towards heads, a 33% chance that I've rigged it towards tails, and about a 30% chance of it being a fair shot, right? And the interesting thing is that this tells you that based on your prior beliefs, given the observation, you should adjust your beliefs in a certain way. But that means that this spiky graph counts very much into what you actually consider to be a realistic probability of this thing happening in the future. So, yeah, what's interesting there is that your prior belief very much affects the belief that you have after the event. And in the case that the event was an unlikely event, your beliefs will be adjusted by quite a bit. And in this case, incorrectly if I had a fair coin. And the strange thing even is that if I had a fair coin and I tossed 3 heads and then 2 tails, that event was equally unlikely to the 5 heads in a row event. Except you're more likely to believe this side because I'm a Java consultant, right? So where does this apply? Well, one thing this applies in is our retrospectives. We look back every 2 weeks. How did we do last week? And one thing you immediately notice there is which of these things were surprising to us. and you start to define action, right? But an interesting question there is, was it actually an unlikely event? And if it was unlikely, how unlikely do we think it was? And what were our prior beliefs about this event before it occurred? So one of your team members may think you need to build a new framework to resolve an issue that popped up last sprint, right? And that could be because in one of their prior projects, they had a situation similar to this one, unlikely event, and their building a framework turned out to be the right solution. So they have a good experience with that. Their prior belief is very heavily biased towards building a framework, also because it's fun. And they might suggest that solution. And you might think, that's a stupid solution. But in order to convey that to him, it can help to point out to him that his prior belief may not have been as realistic as everybody's experience in the room, right? One other thing this can pop up in is service level agreements. We all love those. We want to be 99% up all the time. But a very interesting event happens when one of our suppliers is not up. It actually breaks their SLA. So we had a story where we rely on a Kubernetes cluster provider, and that provider has given us a 99.5% uptime guarantee. And actually, last year, they were down once for 4 days in a row. Now, for those of you calculating, 99.5% is about 1.5 days a year. So they actually broke their service level agreement, and the entire department was furious. They thought this provider doesn't provide quality. We can no longer trust them. They've broken their service level agreement. But an interesting thing is that since that event happened, this event has never happened again. And just because they have a 99.5% chance of being up all the time, or 99.5% chance of uptime, that means there's also a 0.5 times 0.5 times 0.5 times 0.5% chance that they will be down for 4 consecutive days. And nobody asked the question, was this actually a rare event? And furthermore, they did resolutions to prevent this event in the future, right? Anytime we do incident management, we look at how can we prevent this thing in the future. So my entire department is migrating to a different cloud cluster. And it's very interesting because it's a very high cost choice, right? Migrating an entire department of 16 teams to a different cluster. And it may be based on this one event. So one thing to consider there is, do you think this event will happen in the future? And are we biased by our prior belief that this would never happen? All right. One thing that can help you reason about these things is this expected value and utility theory. And if you're like me, by the time you hear value, your face starts to droop a little bit. You're like, here comes another one of those that will say we need to deliver value all the time. But expected value is not like that. It's a bit like gambling, where expected value is basically given a number of repetitions, it's the value that you expect to get out of a bet. And there's some variance. And an interesting thing about expected value is that the word expected is a bit off there. Because let's say I play this game with one of the booths downstairs has this game. They have a jar filled with white and black paper clips. And let's say that if you draw one of these paper clips, if you get a black one, you get $10, you win. If you get a white one, you get $0, you lose. You might base on this picture that your chances are about 50-50, right? So your expected value for this bet, if you only get to do it once, is $5, right? Because you're likely to draw 0.5 times a $10 outcome. So that's actually quite an attractive bet to most people because you have a high chance of winning something. And in software, these are also quite attractive bets, right? Because when you want to build a future, you're not sure if it's going to land or not, but you're quite happy with a 50% chance that it may lead to increased customers, increased revenue, that sort of thing. But then there's also this thing called variance, where let's say you're considering a lottery downstairs, and they have 5,000 participants. Sadly, we don't have 5,000 participants in this room, but let's say the number one lottery winner wins 5,000. Wins 5,000, and then you're going there to get a ticket. But in this case, the expected value is still $5. But you actually only have a 1 in 5,000 chance of winning this $5,000, right? So for you, this might be a more unattractive bet. You might not be conveyed to give your personal information in order to get this $5,000 prize because you're very unlikely to win it anyways. I think in software also, these bets are about how much variance do we have when we're going to deliver this feature. Is it the lottery scenario where it may be worth the investment of $4 and we're expected to get $5 out of it, but we're very unlikely to make that bet? Or is it actually a very likely bet? Is there almost no variance? And do we want to deliver this value that way? You will see that business tends to avoid variance. They want to see what are the features that I can deliver reliably and that will bring me customers. Because they can only invest that money once usually. Software engineering is quite expensive. We don't have the money to make lottery type bets, 1 in 5,000, with our features. So it's interesting that even though the expected value of these two scenarios is the same, you might consider taking the paperclip one over the lottery one, depending on how much money you have to invest. And the other way around, in my current job, we have a lot of push to electrify the grid, because otherwise we cannot bring the Dutch market the energy it needs. So it might be valuable even to take some of these lottery bets, knowing that you're going to fail. So from a business perspective, it matters very much what your outlook is. And an interesting thing there also is utility theory. So expected value was what economists thought the human brain worked like somewhere before 1980. They thought we were all rational agents and that given a good bet, we would take it. And actually it turns out that in most cases we don't. We're a bit risk averse, but also money matters differently to us in different situations. So if you're very rich, then $10 extra from the paperclip game might not mean a lot to you. But if you're actually hungry and looking to buy some food and you don't have any money left on your bank account, then the $10 from the paperclip game may be all you need and may be very valuable to you. So in a different situation, money is valued differently. And the thing economists try to do is they try to market this as utility theory instead. And utility theory states that as you get more and more money, the value of money actually decreases. And you can convert it in this unit that they call utils. And in software we can do the same, actually. So you see, in companies that have a lot of money to spend, they take more risky bets. Because for them, the utility of this money is not so high. They have quite a lot of it. And the utility they get out of the solution could be a lottery bet, but it could be something huge for the company. It could be their competitive advantage, their reason for survival. And actually this also helps us model whether we should take a decision or not in a context where money might not matter. So for instance, there are many people working in government subsidized organizations, working for the tax services, working for the grid like I do, where the budget is fixed. There's nothing they can do about the budget. The only thing they can do is change what they deliver. How many of you are actually working in some sort of non-profit context? Oh, that's quite a few. That's quite very few of you. And that's interesting to me because yesterday also we saw during the CTO talk there's a lot of focus on how much money a certain feature makes. And I think in the commercial space, that's definitely the case. But in a non-commercial space, utility might actually be much more important. How much value are we delivering for civilians? And let's say you're saving 10 minutes of someone's time that's very valuable. So let's say someone higher up in management. That may actually bring you more utility than saving 10 minutes of the secretary's time. Even though the secretary is also a great person and you like them very much, right? Then there's a risk there as well. Because this expected utility and expected value runs the risk of forming a strange type of argument. And we see this, for instance, in security, where there can be a very small risk of something going wrong, but it can cost you your entire business, right? So you would say the expected value of this event, because of it costing you your entire business, is close to negative infinity. So it's very, very large, even though the chance of this happening is very, very small. It doesn't matter because it's dwarfed by the negative infinity of losing your entire business. And an interesting thing that can happen there is that we argue that, for instance, every dollar that we make that is profit should be invested into security because we run the risk of losing our entire business. And these types of arguments will feel wrong to you, right? You'll get a bit of a sense inside that this maybe is not the best approach. And that has to do with the way we consider unlikely events. At some point, we just have to accept the risk. Even though the expected value or the expected utility tells us it's negative infinity or maybe even positive infinity, that's where this expected value starts to behave very strangely, and it may lead to overinvestment in, for instance, security. Or underinvestment in a good case, right? And that leads me to talk about unlikeliness. So, how many of you took the plane here? How many of you missed your flight? Actual 2 people that missed the flight here? No, but missed the flight recently, right? Actually, a very small percentage of people. One of the sayings from an economist is, you should miss more planes. The reason being, if you don't miss any planes, you're spending too much time in airports. And the same goes for software development. You have to look at this unlikely situation, decide what it costs you. Missing a plane is quite emotionally painful, but in reality it's sometimes a 6 or 7 hour delay. But you don't spend all that time in airports. And the same goes for deciding when to start building a feature. So if you accept that you're going to be wrong sometimes and accept the emotional pain there, then you're actually going to end up with a better outcome for yourself, because the event of missing a plane is quite unlikely. I picked a black swan here because for times people believed that black swans didn't exist. It's because they observed so many white swans that they said, oh, it's very unlikely to see a black swan ever, so they probably don't exist. And this reasoning can be quite dangerous. And one of the places it's dangerous is in research. In research, we like to use the null hypothesis, which is to say, I have an hypothesis, and I assume it's going to be true, right? The null hypothesis would be, what is the chance that this thing that my hypothesis is actually not true, and it's just due to random effect, random chance, whatsoever. And usually, we call this significance. And usually we consider research to be significant below a threshold of 0.05. So a 5% chance of actually being left up to chance. The null hypothesis is true. But what we found out was that there's also a publication bias. So when people publish their research, the only way that it gets published is if it's significant. So what happened is they had a, let's say, a significance of 0.06, and they were like, oh my, that's so close to being significant enough to publish this paper. I'm just going to tweak the filters a little bit. And we actually call this, kind of data hacking, to get your paper accepted and get your paper published. And what you see is that actually most published research, therefore, is wrong. Because we tried to get this intuitive measure about unlikeliness, and we gave a value to it to say yes or no. It's a binary value. But it's never a binary value. It's just unlikely that it's wrong. So it's very, very dangerous to reason about unlikeliness. To say something is unlikely, therefore it will not happen. Or to say something is unlikely, therefore it will not happen to me. One thing that's happened in the Netherlands is we had a scandal with the tax services. The tax services in the Netherlands, they were scanning people for potential fraud. And the diagram looked somewhat like this. I don't know actually the numbers of actual fraud detected, so those are made up. They're just for the example. But these are roughly the numbers of the actual tax system. And what happens if you look at this chart is that you see that most of the people, they are innocent. And if you try to calculate what is the chance that an innocent person gets detected as fraudulent when they are not, the chance is actually 0.4%, because 250,000 out of 17.7 million, actually 17.95 million, is a very small percentage. So you could sell this system to someone saying, there's only a 0.4% chance it will detect someone as fraudulent when they're not. But we also need to look at the other distribution. The other distribution of how many innocents we catch to how many we actually catch doing fraud. And the chance there, which is very interesting, is also about 4%. So the chance we have that someone is marked as potentially fraudulent when they're not is actually about the same chance that we have as marking as an innocent person as fraudulent. You would say that's a pretty bad system, right? But if you don't know these numbers up here, you might not know it's a bad system. And an interesting thing there also is that this system was based on observations in practice, right? So it was created using data from actual fraudulent cases in the Netherlands. But what they found out was that the Netherlands has a tendency to check people with a lower income more often, and to check people from a different country more often. So they will actually, in the observations, they found more fraud amongst immigrants and amongst people with foreign nationality and with a poorer income. So that data was inside the observations that they had. But part of that data was because they believed they would find more fraud there. They actually did more checks on those people. And the big companies, they actually lobby you not to check them, right? So it's very convenient for the tax services to check the people that can't actually fight the decision, right? So not only was the system kind of bad, but it also used data that beforehand was biased towards a certain conclusion. So the people here that were marked as potentially fraudulent, but were actually innocent, were mostly immigrants, mostly people of lower education, mostly people of poorer socioeconomic status, and it turned into a huge scandal in the Netherlands. Even though, on paper, it may sound very good if you say it only has a 0.04% chance of marking a person as non-fraudulent when they are not. A last one I'd like to close with is priming. And this one is actually kind of funny because it's in the book Thinking Fast and Slow. And the idea here is that given a certain situation, you're more likely to respond to that same or similar situation faster. And it's used in marketing a lot, where they show you a Coca-Cola bottle, for instance, and you're very tempted to go buy a Coca-Cola bottle. And one of the things it can also do is it can bias you towards certain results. So let's say my manager is having a conversation with me about salary, and it's my yearly review. And he comes up and he starts off, I don't know if this sounds familiar to you guys, but this is what my manager does. And he starts off, Berwout, I think you've been great this year. But when we consider salary, we always weigh what the market does. And we look at what the places around us do. And as we saw, this year inflation was about 8%. Actually there, he was lying. It wasn't 8%, it was 10.5%. I knew he was wrong. But also, I knew that if I said he was wrong, he would get an emotional response which might make him more likely to give me a lower salary. So I let it go. He said inflation was 8%, but we also have to be conservative because things are getting more expensive and the pay that we get for a consultant hasn't grown at the same rate. So if we look at the market in IT in the Netherlands in general, you will find that people on average get about a 4.5% raise this year due to the high inflation. And I'm like thinking, I went into that conversation with an idea. I wanted to have equal or more to inflation, right? Because I wanted to get the better situation for myself. So I was going for 10.5%. But right there, in that conversation, he was priming me to believe he was going to give me a low number. He said inflation is 8%. He said market is doing 4.5% right now. And he comes up to the final number, and I start calculating, right? I start calculating how much percent is that, and I end up figuring out it's 8.5%. And I'm happy. I'm there like, I did pretty good. And then I realize he was priming me to be happy with that response, right? Because he was saying, oh, low percentage here, low percentage there, and then he gave me more than I expected based on that primed result. And the funny thing is, I read that book, he read that book, we had a conversation about that book, so he knows I know he was priming me, right? And I was still happy with the result. So even though you've learned all these things, your intuitive response may still be very strange for the situation. One thing more I'd like to say about priming, there was also a lot in the book about effects of randomly spotting things and then taking them into your subconscious. Most of those studies were actually part of the publication bias dilemma, and they've been not be able to be replicated. So be careful when you read the book. There's actually a guide on the internet as well about how many of the studies were replicated. But Thinking Fast and Slow contains a number of psychological studies that before we figured out that this significance test was not as great as we thought it was, we didn't know that in the past. We accepted the fact that one single study proved that it only had a 5% chance, but there were many, many studies done, right? And many, many people tried to just nudge the data a little bit to give them the right result, right? So many of those studies actually turned out to be false. So read the book with caution and read it with a reading guide. So I think we're about over time here. So I'll give you a brief, very brief overview of what we discussed. We discussed what is meaningful to you as a software engineer, and it will vary based on your context. We looked at how to recognize linear thinking and to be careful of that. We looked at intuitive reasoning about chance and unlikely events causing your perception to change maybe drastically. We looked at utility as a more holistic version of value, maybe even a better predictor of human behavior. And one thing I'd like to leave you with is that unlikely events happen all the time. And inside software, every context is different, and you're going to have to reason about every different situation using your System 2 brain. All right, it was based on these two books. Thank you all for listening, and I hope you have a great day today.